So now we're going to discuss a global energy balance considering now the greenhouse gas effect. So before that, we had a model that was the zero energy model that allows us to understand how much, what would be the baseline temperature that we will have on Earth without considering this effect, right? So now that we can consider, we're gonna make a balance, an overall balance on how much is absorbed, how much is reflected, and how much is going to following other processes that are very important. It is worth mentioning that this global energy balance, it's been always, it keeps updating. So this is the current, this is the one that I'm discussing now, is the one from the IPCC of 2007. But there are some others that are before, and they will have some variations on the values, right? So now that we have this overall balance, we're going to start discussing the amount of incoming solar radiation. The value that we have here is 342 watts per square meter. Let's go back to remember that we have the incoming solar radiation that we discussed before was 1,370 watts per square meter. When we were using this value, we were using it to estimate the total amount of energy that was entering into the Earth, assuming that the Earth, the area of a circle, right? To really distribute along the whole planet, we're going to divide this value, the 1,370, by the surface area of the Earth. So the area considered like as a sphere. So if we do that, we come up with this value, with 342 watts per square meter. And then we need to consider the albedo to know how much energy is actually being reflected from solar radiation. So since the albedo is 31%, the amount of incoming radiation reflected back into space per square meter of the Earth's surface is the solar energy reflected divided by the surface area of the Earth again, and then multiplied by the fraction, the albedo, right, the 0.31. And this come up with the value of 107 watts per square meter. Of this value, it is estimated that 77 watts per square meter is reflected off the space, the atmosphere itself. The solar radiation that is not reflected is absorbed by the Earth and its atmosphere. Calling that, we will be calling this absorbed energy, QAFs. Again, with units of watts per square meter of surface. So this gives the solar radiation absorbed divided by the surface area of Earth will give us the value of 235 watts per square meter. Of that value, 67 watts per square meter is absorbed by the atmosphere, and the remaining 168 watts per square meter is absorbed by the surface of the Earth. If we assume that global temperatures are unchanging with time, then the rate at which the Earth and its atmosphere receives energy from space must equal the rate at which energy is being returned to space. The 107 watts per square meter of reflected energy is already balanced. That is, 107 watts per square meter hits the Earth's atmosphere, and 107 watts per square meter is reflected back into space, so we can ignore that component for now. The Earth and its atmosphere absorb the remaining 235 watts per square meter. So the same amount must be radiated back into space. So this is where the balance is not going to be match what goes in goes out, right? Because so if we will be radiating the same amount, the 235 watts per square meter, we will come up with the number of 254 K of temperature, minus 19 degrees, right? If we will be based on the zero balance model that we discussed before. But now we're going to introduce the greenhouse gas effect. And we will assume that part of this energy will be absorbed in the earth, right? So therefore, to force enough energy through the atmosphere to create the necessary balance, the temperature of the Earth's surface must be higher than 254 K, right? And we can actually estimate this amount going into another direction by looking at the temperature of the surface. But let's look at how are we going to now get this balance in the way of in terms of energy budgets. So if we treat the Earth as a black body radiator, we can use the previous equation to estimate the energy, right? But now we know that this is not a black body. So now we're going to consider the energy radiated by the surface divided by the surface area of Earth. And we will come up with 390 watts per square meter. From that, only 40 watts per square meter passes directly through the atmosphere. And then we discussed that it will be passed through this window. Remember the atmospheric radiative window that we were talking about. But the remaining 350 watts per square meter is absorbed by greenhouse gases in the atmosphere. So the atmosphere then radiates 324 watts per square meter back to the surface. And then there is also some heat transfer from the surface to the atmosphere by convective heating, evaporation, and condensation of water. So that's why we were discussing. We have said that one of the most important greenhouse gas is the water, but the water also have other processes going on that can absorb energy, right? Okay, so convection transfers 24 watts per square meter to the atmosphere, and then condensation of water provides 78 watts per square meter of latent heat. So what we can do now is we can see, we can make a balance now of the rate of energy gain and the rate of energy loss. The difference should tell us if there is a gain in energy or there is a equal amount of energy going in and out, or there is a decrease of energy, of the Earth is losing energy, right? Okay, so we can put all together all these values and to make a simple balance, right? And discuss how much energy in total we are gaining. But to skip an overall balance with all these numbers, we can also have a rough estimation only looking at the top numbers. That is the energy, the balance on space, what goes back to space and what goes in. So we can look at only the reflected solar radiation, the incoming solar radiation, and the outgoing long wave radiation. By looking at these ones, we have what goes in, which is only the incoming solar radiation, equals to what goes out, which will be the reflected solar radiation and the outgoing long wave radiation, right? By looking at this, we come up with a number that is a positive number, right? And that is telling us that we're gaining energy, right? And you can make you can estimate this number